Okay, if you've ever had to deal with stubborn scale buildup in hot water pipes or industrial boilers, you already know that water hardness is a massive deal in civil engineering. Today, we're breaking down exactly how to measure it using the standard EDTA method. This explainer is going to get you perfectly prepped for your environmental engineering lab.
First up, what exactly are we hunting for here? Well, hardness is basically the concentration of multivalent metallic cations. Mostly, we're talking about calcium and magnesium, just sneaking around in your water. Now, to keep things standardized globally, so we're all speaking the exact same chemical language, we mathematically express this total concentration as milligrams per liter of calcium carbonate.
All right, before stepping up to the bench, you're going to need to gather your standard glassware, a burette, a pipette, and a conical Erlenmeyer flask. But the real stars of the show here are your reagents. You'll need a standard 0.01 molar EDTA solution, an ammonia buffer solution locked in at a pH of 10, your distilled water, and of course, your chemical alarm system, areochrome black tea, or just EBT indicator.
Now, here is the brilliant visual chemistry that makes this whole titration possible. When you add that EBT indicator, it forms this weak, wine-red complex when it binds to the metal ions in your sample. But EDTA acts as a chelating agent. Think of it like a microscopic molecular claw. As you add it, it literally steals those metal ions away to form a much more stable complex. And once every last ion is stolen, the EBT is freed up and boom, the solution instantly flashes to a clear blue.
But there is a catch. This reaction only works if we lock the pH at exactly 10 using our buffer solution. Give or take 0.5, but really keep it right at 10. Why? Because if the pH drifts too high, those calcium and magnesium ions will actually precipitate out as solid calcium carbonate and magnesium hydroxide, and that will completely ruin your titration before you even finish.
So how does this actually play out at the bench? Step by step, you'll first rinse and fill your burette with that 0.01 molar EDTA. Next, pipette a precise water sample, usually 20 or 50 milliliters, right into your conical flask. Then add 1 to 2 mils of that absolutely crucial pH 10 buffer. Finally, add just a pinch of the EBT indicator and watch for that distinct wine-red color to develop.
Okay, now for the main event, the titration process itself. First, record your initial burette reading. Then, carefully drip the EDTA into the flask while swirling it continuously. And listen, as you get close to the endpoint, slow down. You are looking for a sudden, highly specific endpoint where the wine red flashes to a crisp, clear blue. The second that happens, stop. Record that final reading and repeat the whole thing until you get consistent, concordant values.
You'll be logging all your initial and final burette readings in a standard observation table. Notice how absolutely crucial it is to track the exact volume of EDTA used across multiple trials. Honestly, consistency here is what separates a rough guess from valid, usable engineering data.
All right, with your concordant data in hand, it's time for the math. And it's pretty straightforward. You just plug your EDTA volume into the total hardness formula. Take the volume of EDTA used, multiply it by its molarity, which is 0.01, and multiply that by 100,000. Then, just divide that whole shebang by your original water sample volume. And there you have it. The result is your total hardness.
Remember though, your final result, expressed in milligrams per liter as calcium carbonate, isn't just some abstract lab exercise. It's an environmental reality. It tells us the exact total divalent cation concentration. And that allows civil engineers to predict severe scaling risks, prevent catastrophic industrial pipe damage, and figure out if municipal water supply needs immediate softening treatment.
Determination of hardness of water by EDTA method. Well, you now have the chemistry, the procedure, and the calculations totally locked in. The next time you see a massive water treatment facility or a scaled-up boiler, you're going to know exactly how they measure the culprit on a molecular level. So as you gear up to step to the bench for your own environmental engineering lab, I have to ask, just how accurate will your very first titration be?